hypothesis testing. So moving right along to hypothesis testing. Hypothesis testing. So we can conduct hypothesis tests using the confidence interval approach, and we've already discussed that, but we can also use a null and alternative hypothesis. So sometimes you wish to test the null hypothesis, that mu is equal to some value against the alternative hypothesis that the true value does not equal some value. So mu is the population mean, and we estimate with y bar. So we can think of c as some temporarily assumed value for mu, and we can compare a sample statistic to this sort of temporarily assumed value to see if we have strong sample evidence that the true value is something different than the hypothesized value, in this case c. So if our sample statistic has a normal distribution, and it does, so here we're talking about the distribution of the mean. So if our sample statistic has a normal distribution, we can temporarily assume that the true value is c, that the true value is equal to c, and then we can compare. So we're saying that that mu is equal to c, that the true value is equal to c. I can grab a sample, solve for the sample statistic, and then I compare the sample statistic to the true value. And of course, if my sample statistic is very, very large relative to c, then that's evidence against the null hypothesis. So I might reject the null hypothesis and make the assertion that mu is different than c. So again, this is just hypothesis testing. When we see examples, it'll make a heck of a lot more sense. Also remember, y bar and s are the mean and standard deviation of a sample of size n that has been randomly selected from the population having mean mu, and the t-value is simply equal to, in the context of hypothesis testing, y bar minus c divided by the standard deviation divided by root n. So if our sample statistic has a normal distribution, we can see how far our sample statistic is from the hypothesized value. We can basically compare y bar. If we get a y bar that's way out here, we can basically say, you know what, that's different than the hypothesized value. But we perform this comparison using the t-score. So we normalize our sample statistic. In this case, the normalized mean is 0. And if we get a t-value, or a normalized sample statistic, that basically we temporarily assume that c is equal to mu. So if c is equal to mu, and I get a value much larger than c, this numerator is going to be very, very large. And remember, if that difference divided by s over root n is something like 4 or 5 or 6, basically what we're saying is that the observed value is 6 standard deviations from this temporarily assumed value. So if we assume that the true value, mu, is equal to c, but we see a sample statistic that is much, much larger than c, we might reject this null hypothesis. On the other hand, if the sample value is very, very close to c, we might not, and then when I say very close, what specifically do I mean? When I say y bar is very far from c, what specifically do I mean? I mean close and far in terms of standard deviations. Now we're talking about a sampling distribution, so standard errors. So if we are 3 or 4 or 5 standard errors away from the hypothesized value, this temporarily assumed value, we might reject that hypothesis. But if we are very, very close, maybe 1/2 standard, like if we're very, very close to the hypothesized value, we will fail to reject the null hypothesis. You know, one of the things that we learned is that the sample mean is an unbiased estimator of the population mean. So even though the sample mean does not equal the population mean, the average of all the different sample means that we could have calculated is equal to the true population mean. Also, if the population is normally distributed, then we know that the sampling distribution of the mean is normally distributed. And once we know the sampling distribution of the mean, we can make those probability statements about sampled values versus hypothesized values. So again, if the sampled value is close to the hypothesized value, in other words, if we get a small t, then we're not going to reject the null hypothesis. But if we get a sample value that's far from the hypothesized value in terms of the number of standard errors from the hypothesized value, we might reject the null hypothesis. In that case, we have statistical evidence that the population mean is very different than the hypothesized value. So you guys have been through sampling, you guys have been through hypothesis testing before while working on your, while working through your first statistics class, but this is a nice review. So when we see some examples, this will make more sense, but again, if the t statistic, we're going to be solving for this t, and if this t-stat is very large, this provides evidence to support rejecting the null hypothesis. Basically, what's going to happen is that the firm is likely going to have to intervene in some way, shape, or form. All right, let's review what a type 1 error is and a type 2 error, and then we'll sort of move on to examples. A type 1 error is committed when we reject the null hypothesis when it is in fact true. So if we assume that the null hypothesis, or if we temporarily assume that mu is equal to c, and we get a sample value that is very large, let's say we get a sample value past the critical value, which includes, 2.5% in each tail, that's going to happen 5% of the time by chance. So just because we get a very large sample statistic relative to the hypothesized value doesn't necessarily mean with 100% certainty that mu does not equal c. In other words, we don't accept the alternative, we just reject the null. In other words, we've got evidence that says that mu does not equal c. We're not saying that mu does equal c. And if we specify the level of confidence to be 5% or the level of statistical significance, if we specify alpha to be 5%, or we put 2.5% in each tail, so the level of statistical significance is 5%, then we are going to randomly get values, sample statistics, that are greater than the temporarily assumed value of the hypothesized value 5% of the time. So even if the null hypothesis is true, we're going to reject it 5% of the time. So that's really important to understand. So very quickly, if the population is normally distributed, and we know that it is with mean mu, we can reject the null hypothesis that mu is equal to c in favor of the alternative hypothesis that mu does not equal c by setting the probability of a type 1 error equal to alpha. So here is what alpha, so that's what alpha is. It's the level of statistical significance, and it's equal to the probability of committing a type 1 error. And again, this is something that we choose. We might feel comfortable with an alpha equal to 0.5. In other words, if we're wrong 5% of the time in the social sciences, we can live with that. So if we solve for t and we see that t is greater than the critical t-value that includes alpha divided by 2 in the upper tail, 2.5%, or if we see a t that is less than the critical value, so less than the critical t-value, that puts 2.5% in the left tail. If we observe a t greater than the critical t or less than the critical t, we can reject the null hypothesis. Again, the level of significance tells us that when we reject the null hypothesis, we're still wrong 5% of the time. So if we want to be wrong only 1% of the time, we need to change alpha to 0.01 or 1%. A type 2 error is committed if we do not reject the null when it is false. So if we fail to reject a false null, we commit a type 2 error. There are different things that we can do to control the probability of a type 2 error. That's a little bit advanced. We won't get into that. But we can choose the level of statistical significance, and we can pick the probability of a type 1 error. Typically, in the social sciences, alpha is equal to 0.05 or 0.01. Sometimes for certain problems, we might set alpha equal to 0.1. All right, so recall that if the population sampled is normally distributed with mean mu, then the population of all possible values of y bar minus mu, but divided by the sample standard deviation divided by the square root of n. So if we replace that sigma with an s, so y bar minus mu divided by s divided by root n, these values, or t values, follow a t distribution with n minus 1 degrees of freedom. So it follows that if the null hypothesis is true, then the population of all possible values of the test statistic t is equal to y bar minus c, our temporarily assumed value of mu, has a t distribution with n minus 1 degrees of freedom. So again, we can find those critical t's and compare the calculated t's to the critical t's to determine whether we should accept or reject a null hypothesis. So these are the steps to hypothesis testing. Actually, I probably should have just started with going over the steps. So the steps to hypothesis testing are, first, you state in advance the level of significance. You have to pick that in advance. You state in advance the decision rule, or the null and alternative hypotheses. You compute your test statistic. Then you compare the test stat to the critical stat, and then you use that information to determine whether or not to reject or fail to reject the null. We don't accept it. We either reject it or we fail to reject it. All right, so let's do an example, and we're going to assume a significance level of 0.05. So let's say this corporation takes a random sample of n is equal to 6 bottle fills. So these are bottle fills. So again, when we do examples, it just makes a heck of a lot more sense. So we're taking 6 bottles. We're taking a random sample of 6 bottle fills from its bottle filling process. So we're thinking about some sort of a business process improvement example. And we want to state the null hypothesis that mu is equal to 16 ounces. And the alternative hypothesis is that mu does not equal 16 ounces. So why would we state this sort of hypothesis? So let's say that we get a sample comprised of 6 bottle fills, 15.68, 16, 15.61, let's say that we get a sample comprised of these values. So I'm going to clear the data and I'm going to input this fills variable. I'm going to list, and these are our 6 sample values: 15.72, 15.86, 15.93, 15.61, 16, and 15.68. So we take this random sample and this is what we get. What do we do next? Well, from this sample, we can solve for the average. Let me do that very quickly. So I'm just going to put SU for summarize, and we see that the average is 15.8. Now, what are we hypothesizing? That's a little low. This is a bottle filling process. We want to make sure that our customers get 16 ounces. If we're getting 15.8 with this standard deviation, do we have a problem? So let's see. We have to solve for the critical t-value. We know that if I standardize this number, this 16, it follows the t-distribution, so we can compare the calculated value to the hypothesized value. We know that the standardized mean is equal to 0. So if we temporarily assume that the true mean is 16, then 16 minus this temporarily assumed true value divided by the standard error, whatever it is, s divided by root, if we assume that the temporarily assumed value is equal to the hypothesized value, we get a 0 for the mean, and we can compare the critical value to the critical t-value to the calculated t-value, or the normalized value for bottle fills. That's what the calculated t-value is. So we're going to put 2.5% in the left tail, and we're going to put 2.5% in the right tail. We know that n is equal to 6. So if n is equal to 6, what is the critical t-value? Well, let me open up my t-table and we'll check it out. So I've got stat tables here, and this is my t-value table. This is my t-table, and we've got a sample of 6. So if I go to degrees of freedom equal to 5, and we're going to let 2.5% exist in the upper tail, the critical value is 2.571. So the critical value, T critical, is 2.571, and since it's symmetric, it'll be negative 2.571. But the negative amount isn't really meaningful, so normally we would conduct a one-tailed test in this case, and we can do that in just a second. But we have to compare the critical value to the calculated value, and remember the calculated value is, or actually this negative will come into play now that I think of it, because we got a sample mean less than the hypothesized value. So basically what we need to do is standardize our sample mean. So if I go to state, I see the sample mean is 15.8. So remember, the t-value is equal to the sample mean minus the hypothesized value, all divided by s divided by root n. And we saw that the standard deviation is 0.1532. We know that n is equal to 6. We know that y bar is equal to 15.8. That's going to be 15.8, and we know that we are assuming 16. So let's solve for this t. So the t is 15.8. And again, basically what we're doing is subtracting out the temporarily assumed hypothesized mean and dividing by the standard error. So we're going to see how many standard errors our sample statistic is from this temporarily assumed value. So in other words, we're just going to solve for a standardized measure of bottle fills. or this particular sample of bottle fill. So 15.8 minus 16 divided by 0.1532 divided by the root 6. If you solve for this, you will get negative 3.2. Now, since the absolute value of this is greater than the critical t-value, or since negative 3.2 is less than negative 2.571, in other words, the calculated value is less than the critical value, we won't observe this if the true hypothesized value, or if the hypothesized value is true. In other words, if it's really 16, once I standardize it, very rarely will I observe a sample value that is 3.2 standard deviations from the hypothesized value. I'll observe that less than 5% of the time if the cumulative area in both tails is 2.5%. So the p-value is the probability that I observe a sample stat at least as large as that observed given the null hypothesis is true, and we know that's less than 5%. Basically what we're saying is that following the steps, the rule says that if this is less than the negative 3.2, the calculated t-value is less than the critical t-value, we reject. We reject the null hypothesis. So how do we do this in Stata? Well, I love it. In Stata, you just put t-test fills is equal to, and then you put the hypothesized value, and you see that the t-value is negative 3.2 about, and everything that we got, Stata gives automatically. So if I do this in Stata, it's really that easy. That is all that we really need to do for the statistics review. I'm going to go and go through the rest of the notes, but as far as the Stata program is concerned, I can put exit here, and I will have completed nearly everything in the notes. If I run the entire program, Stata is running. We've worked with some pretty big data, so that's why it's taking a while. And remember, we wrote this do file so that a log was created equal to statreview.log. So if I view statreview.log, I get everything that was produced by my program. So we get all that wonderful stuff. All right, so moving right along, we can also do a one-tailed hypothesis test. Again, it's the same process. The only difference is how you write the null and alternative hypothesis. And this is something that we are going to do in class quite a bit. But we might write the null hypothesis if it's a one-tailed test. In other words, if we have reason to believe that the true value is greater than some hypothesized value, put what you believe is the case in the alternative hypothesis. So we might say that mu is greater than 30. The equal sign always shows up in the null, and I could put mu is equal to 30 there, but since I'm using greater than in the alternative hypothesis, I'm going to put less than or equal to 30. And basically what we're doing is we're taking all of the area under the t-distribution. Instead of dividing it between two tails, I'm going to put that full 5%, the full 5% in one tail. If that's the case, like in our previous example, if we had degrees of freedom equal to 5, but we put all 5% in the upper tail, the critical value goes to 2.015. That makes sense, right? If I take this percent and put it in here, in other words, I'm taking some of the percent from this side and I'm putting it all on this side, then I'm going to move to the left a little bit, and my critical value is going to move to the left. And instead of 2.571, we're going to get, I forgot what it was, but with 5 degrees of freedom, 2.015. 2.015. So that would be 2.015. So I put 2.015 there as my critical T. So that's the T alpha, not alpha divided by 2 because it's in one tail. I still got my degrees of freedom. That's the critical. And then I solve for the sample statistic. Let's say I get a sample statistic equal to 2.132. Well, it's greater than the critical value. I reject the null. I have statistical evidence that it's greater than 30. So how do we do this in Stata? It's really easy. We'll use the miles per gallon data. I'm going to summarize miles per gallon. I see that the mean is 31.2. I'm going to temporarily assume that the mean is equal to 30. So I'm going to put t-test miles per gallon is equal to 30. Boom. I solve for the calculated T. Oh, my bad. In this data set, we have 4 degrees of freedom. So the calculated value is 3.56. The critical value with 4 degrees of freedom and 5% in one tail is 2.132. So this, in the example in the notes, is 2.132. And then the calculated value, so that's the critical value is 2.132. The calculated value is 3.569. And since that calculated value is greater than that critical value of 2.132, again, we reject the null hypothesis. I know it's super easy. You can also include in the alternative hypothesis that the mu, the true value, is less than some hypothesized value. Again, this is something that you can do in Stata fairly easily. We're going to use Phil's clear list. And I'm going to summarize Phil's, and it's 15.8. Oh, I'm sorry. I'm looking at the p-value. The last example in the notes explains the p-value. So example 7 is just another example. I don't think the data is in Stata. So you can just read through example 7, but we're just basically saying that the alternative hypothesis is mu is less than something, 60 in this case. And again, if we are including in the alternative that mu is less than something in the null, it's going to be greater than or equal to. The equal sign always shows up in the null. And we're going to compare the calculated value to the sample value. The calculated value is greater than the sample value. I'm sorry, if the calculated value is a larger negative number than the critical value, we're going to reject the null, and that's the case. And then the p-value, we already said that the p-value is the probability that you observe a sample statistic as large as that observed, given the null is true. And the p-value is given to us in Stata. So this is the null in our previous example, that the mean is greater than 30. The probability that we see a value greater than the hypothesized value given the null is true is less than 2%. So in our Phil's example, we did the t-test that Phil's was equal to 16. The mean was equal to 16. And here we get a p-value that, again, that is less than the critical value. So if the p-value is less than the critical value, and this is what we're looking at here, but if the p-value is less than the critical value, then what we are going to do is reject the null hypothesis. The p-value is just the probability that we would see a sample mean equal to 15.8 if the true value is 16. So if the probability that we see a sample value this small, if the null is true, is only 2.41%. In other words, this is so rare, this sample statistic is so rare, we only get it 2.41% by chance. And that's too low. We're going to reject the null that the mean is equal to 16. There's something wrong. The firm is going to have to intervene. We're going to have to change the specifications on the machine and make sure that the ounces increases a little bit. We want to fill up these bottles a little bit more so that we don't have mad customers. All right, so that is the stats review. I probably should have done this in multiple sittings, but you can always, pause it, come back to it, review the notes as you see fit. You may or may not need to do the stats review, but if you do, it's been recorded. I hope this helps. If you have any questions, please feel free to reach out. All right, have a good one.